Good morning, good evening, good afternoon, wherever you are on this planet, and welcome to our SETI Live. My name is Franck Marchis. I'm a researcher at the SETI Institute and the Chief Scientific Officer at Unistellar. So today we are going to have a 30 minutes conversation on the recent discovery announced by NASA based on JWST observations of a main-belt comet, specifically one main-belt comet called Comet Reed. The article published in Nature suggests the presence of water and the absence of carbon dioxide. And we are going to talk about this and the importance of this discovery for the field of astrobiology. And for that, I invited Mike Kelley. Hi, Mike. How are you?
Hello, I'm great.
Where are you located, Mike, right now?
I'm at the University of Maryland in College Park.
All right. Well, welcome to our SETI Live. I think it's our first SETI Live together. So
Yes.
I'm glad to have you. We met recently in December at the JWST conference on first results at STSCI, and I remember you presented this work, and I knew that it will be an important work. So I'm glad we have you here to talk about that. I remind our viewers they can tell us where they're watching us from. And let's start. Let's take the stage. I really want you, Mike, to take the time to talk about main-belt comet. What are those things?
Yeah, main-belt comet. Yeah, that's an interesting term. So there's two parts to this. This is an object that lives in the main asteroid belt, but is a comet. So if I could show my first slide, I just have a couple images. This is what an asteroid looks like to us in a telescope. It's just a point in the middle of a star field. It actually moves with time. So if we took another picture and with it, a minute later or an hour later, this point that's in the center of the box would actually be in a different location. And that's how we know it's an asteroid and not a star, because it's much closer to us. And the stars being much farther away don't move. But since the first asteroid was discovered in 1801, this is all we knew about asteroids. This is what the basis of our knowledge of asteroids was as asteroids as points of light. In contrast, a comet is much more
interesting.
Yeah, it's different. The comet is the bright object on the left is actually Mars. So that's another interesting object, but for another day. But this comet, which is a comet ZTF, which people may remember from the beginning of the year, has a tail, has two tails, and it has this green glow about it. They're extended objects, and the reason that they're so different from asteroids is because of the presence of water ice, carbon dioxide, and other volatiles. And these things are warmed by the sun, and they erode when they're warmed up. They turn from ice into vapor, and that vapor escapes and causes the surface to erode, and that's what produces the appearance of a comet.
Yeah, so, maybe to make sure that people understand, maybe you can show a close-up picture of an asteroid and of a comet, so we have a better idea of what we are talking about.
Yeah, right. So in the telescope, this is what asteroids and comets look like. I can skip ahead to, let's see, like this. So this is what an asteroid looks like up close. Mm-hmm. This is actually a very large asteroid, about 100 miles across, or 100 kilometers, give or take. You see lots of craters on it.
It looks like the moon surface, basically.
Yeah, exactly. Mm-hmm. But also very different from the moon. It's irregularly shaped. The moon is quite spherical. This one is not. So it's an object that is its history is controlled by impacts because it lives in the asteroid belt. This is this region between Mars and Jupiter where most asteroids spend their time. In contrast, if we looked at a comet up close, and now being in the space age, we're able to send spacecraft to these objects and take images of them up close, which is fantastic, and study them in detail. So here's a comet. This is Comet 67P Churyumov-Gerasimenko. Both of these objects, the asteroid and this comet, were imaged by the Rosetta mission, the European Space Agency mission that visited them. But here, you can see the terrain is very different. There's lots of rough textures as well as smooth regions. Distinctly, there's no craters. There do happen to be things that look kind of crater shaped, but they're not impact craters. And you could see those in a different image, maybe not this one so well. But also, you see that material, that dust material being lifted off the surface and escaping.
Yeah, we see this jet, basically, which is due to the vaporization of gas that carry with it dust particles of the interior of a comet. So that's an asteroid, that's a comet.
Right.
Okay? But then there is also a difference in the orbit that
yes.
We can go through.
Yes, right. So here's a kind of a diagram of our solar system out to Jupiter. So the sun's at the center, then the interior planets, Mercury, Venus, Earth, Mars. Then there's a kind of a diagram of the asteroid belt as all these little points of debris outside of the orbit of Mars, and then Jupiter. And Jupiter also has asteroids that coexist in its orbit, although they don't get very close to the planet. They do orbit at about the same distance. So this is where most asteroids are in our solar system, is in this region between Mars and Jupiter. It's a warm region of the solar system. It's close to the sun. Not as close as the Earth, definitely not as close as something like Mercury. But some asteroids we do have near Earth asteroids in our solar system, and they are a concern. But that's a small population compared to what's in the asteroid belt. We know of 1 million asteroids, and almost all of them are in this asteroid belt. So the difference for a comet, at least the comets that we've known throughout all of history, is that they come from the outer solar system. So this is a diagram that's showing the comet, just an example of what a comet orbit might look like. It comes from farther away from the sun, crosses the orbit of Jupiter, and may even get to closer to the sun than the Earth. Some of them do, some of them are farther away than that. And then goes back to the outer solar system. So because of the differences between the orbits between asteroids and comets, we can tell that comets come from the region of space out near Neptune and farther. And that gives them an opportunity to be cold, or they are cold for the history of the solar system. They stay cold, unlike these asteroids, which are warmed by the sun because they're so much closer. So that gives them a chance to save the ices that they accumulated 4.5 billion years ago when our solar system was formed.
Okay, so what are those MBC, those main belt comet?
Yeah, now that interesting term, main belt comet. So in 2006, astronomers discovered a class of comets called main belt comets. These are objects that have orbits in the asteroid belt. They live in the asteroid belt. So they look indistinguishable from any other asteroid just based on their orbit. But they behave like comets. They show a tail. They repeatedly show a tail every time they're closest to the sun. They just get a little bit closer, a little bit farther, but they do have a slightly eccentric orbit, what we call it. So that suggests to us, they have all the behaviors of comets, but the orbits of asteroids. So that's where we call it the main belt comet.
Mm-hmm. Okay, so before we go in more details about the main belt comet, let me say hi to some of our viewers. We have Thor from Sweden, Alan Gross from New Jersey. Alan requests we do this at 2 p.m. instead of 2:30 p.m. Send us an email explaining to me why you want this at 2 p.m. instead of 2:30, and we may change the time just for you. We have Paul from Toronto, Jonathan, say hi, the Piper from Northern Maine, Florida, people from Florida, from Dorset, England, from New Jersey, Eugene, Oregon, South Florida, Ankara, Turkey, Tierra del Fuego in Chile or Argentina, it depends, but hello, everybody. So you are watching us, this is a SETI Live, and we are talking about main-belt comets with Mike Kelley. So Mike, we know now, I would say a dozen of those main-belt comets, something like that, right?
Yep.
And a year and a half ago, maybe 2 years ago, you wrote a proposal with other people and to observe one of them called Comet Read, 238p/Read. We're going to call it Comet Read because it's easier for everybody. So tell us a bit why we chose this target specifically.
Right. So there's two parts to this question. One is we were interested in studying one of these main belt comets with JWST, and we wanted to study its activity. We wanted to see that tail. We wanted to see it eroding away. So we needed to find a comet, one of these 12 main belt comets, close to the sun and active, or closer to the sun when it is active. So that's the first part of the problem. The second part of the problem is that the Webb telescope has this giant sunshade on it, and that's to protect the telescope and protect all the instruments. They can't get warm. If they get warm, we don't get data. Let's say that. It's very bad. We can't have direct sunlight on those instruments, and we have to keep them stable and cold, and that's a very key part of the instrument's design. So because of that, it's limited. It can't point anywhere in the sky at one time. It can point to approximately like a right angle, like 90 degrees away from the sun. So we originally proposed for this. Oh, I can't even remember, 2018. it was a while ago. And we picked the best comet at the time. And we thought that was the one we would observe. The telescope launch schedule had changed because of various reasons. So that we had to change our target. And I think I think we only changed targets once. I have another program where this was a little bit more complicated, and I changed targets multiple times. But this particular Comet Read was our second choice, not because it was any better or worse than anything else, but because it was the one comet that could be observed if JWST launched in 2019, which it did.
Okay.
2021. Yeah.
It's getting confusing.
It was going to launch in 2019.
All right, let me go back to this later. In a few seconds, say hi to people from Denmark, Australia, France, Texas, Bali, Nishiharima in Japan, Maine, USA, and Montreal. So welcome. So you use JWST with the goal of better characterizing this comet. In astronomy, characterizing means like getting a better idea of the composition in gas, but also particle temperature, size of the nucleus, and all of this. I'm assuming you wrote a very detailed proposal claiming you're going to do a lot, and then what happened? You get the first data. The first observation was taken in I forgot the date exactly.
This was September 2022.
Right.
Yeah.
So tell us a bit of the details of you observed with near spect. So maybe expand a bit near spect and what you did with those observations. You can show them too if you want.
Yeah. The first thing was we took an image. We took two things. We took an image of the comet and we also took a spectrum. So if you could show the image. So here's our image. It's not color. The color is not blue, but it's just colored blue for artistic purposes. It's actually just a black and white image. But here's our comet. Now it's not like that amazing comet ZTF that I showed earlier with the two tails and the green glow of gas. That's because this comet's faint, and we actually wanted to spend more time taking spectroscopy data rather than imaging data. So we took a brief image just to see what it looks like. and this is it. So it has a bright core. It was active. It was losing dust, and that dust was being pushed away by the sunlight into a tail. But the purpose of this program, the purpose of these observations, was to take a spectrum. Now, the spectrum is the exciting thing for me. That's what we can break down this light that we're seeing here and try to understand the fingerprints of the molecules that make up this comet. So here it is. Here's our spectrum of Comet Reid. And I have also, for comparison, a spectrum of a more normal comet, Comet Hartley 2. Reid is the white squiggly line, and Hartley 2 is the blue squiggly line that's higher up. And we're looking at infrared light. So this is a region of the spectrum of the light. These are light frequencies that we can't see with our human eye. They're beyond red. They're redder than the reddest thing that we can see with our eye. But that's a key wavelength range for comets because it has signatures of water gas. The number one ice in comets is water ice. It's the most prominent ice in all the comets. Well, in the comet population. And what we see around this comet is water gas, right there between the wavelengths of 2 and 3 on this plot. And it matches really well with what we see with Hartley 2. It's at the right wavelength position. The shape's a little bit different, but there are important science reasons for that. But it exists. And so this is what we wanted to do. We wanted to study how much water this was losing.
Yeah, so I just want to clarify to our viewers that we did believe for a long period of time that main-belt comets were in fact had the same kind of activity than comets. But this is the first time we have the definitive proof that main-belt comets are comets.
That's right.
Activity.
Yeah.
The detection of water. These
comets are faint. So they're not the kind of comet you would see with a backyard telescope. And in fact, it's been 15 years since the first attempt to detect any gas. So we could see dust, but we couldn't see gas. We've tried to observe gas with the largest telescopes on Earth. Mm-hmm. And yet there was no detection of gas. It was at the level where, it could still be a normal comet, with just the gas was too faint to see. Or perhaps we have to go back to the drawing board and think, well, maybe there's some other reason that these things are losing mass and it's not actually ice. But ice seemed like the best case. So that's
that's important for people to understand the way science works. Mm-hmm. I mean, we have a hypothesis. We discover something weird. So then people came with theory, hypotheses, and so on. And then we have courageous observers like you, and I'm one of them too, that write proposal to try to confirm whether or not those hypotheses are right or wrong. It's very difficult to get time. This doesn't look like, I know you summarize this by saying, oh, then I asked for time and I got time. It's not that easy. You have to prove, you have to write a proposal, you have to convince people. And then you got this data, and with this processing, it's clear now, it's unambiguous that main-belt comets have eject water gas. And that's an important part. Similarly to other comets that we have seen, like Hartley 2 that you just showed. But there is one thing also, another type of mystery in this spectrum that we can go through. Maybe you can show the spectra. There is something weird that we are not expected here. So what is this?
Yeah, so the other part of this is that carbon dioxide is the second most abundant ice in comets. Water is number 1, carbon dioxide is number 2. There's about 20% of carbon dioxide as the amount. There's about 20% as much carbon dioxide as there are water in the comet population. So when we look at the wavelengths where carbon dioxide should be, we see nothing at Comet Reid. And you can see that as the red shaded region between 4 and 5 here. Whereas in Hartley 2, a more normal comet, we see a nice bright carbon dioxide line or band. So where's that carbon dioxide? So that's where the key about main belt comets comes in. So this is just a very different object from all the other comets that we know about and that we've studied before. And it's really a matter of temperature. You know, water ice is something that we can touch here on Earth, and it's safe for us to do so as long as it's not too cold. Carbon dioxide ice, or dry ice, is very cold, and it's not something you want to touch, or for very long anyway. It's a much colder ice, and sublimates or vaporizes at lower temperatures. So to say that it's missing in Comet Reed means that, well, perhaps this is an object that formed in a warm location of the solar system, so that there was no carbon dioxide ice available to actually make up that object. Or a second case is that Comet Reed actually is a normal comet from the outer solar system, and it's just spent such a long time around the sun in the asteroid belt that the carbon dioxide has warmed enough and has been lost. But the water ice was not so volatile, and it could actually stick around. So that's the mystery right now, is which of those scenarios actually describes Comet Reed, and is it all main belt comets are the same?
Is it something intrinsec to the formation, or that's a result of the evolution? And that's a question that you are now asking, and I read your paper, and that's also mentioned in the scientific paper that is available, by the way, for those who wants to read it. We have the description we have the link in our description, the description of this video. We're getting questions, so I have a lot of questions for you, but I'm going to take the time to take a few questions from the audience first. What instrument did you use, and why this one? That's something from Julian Pompeo.
Yeah, this is the near spec instrument on JWST. And that's the one that covers these key wavelength ranges.
Between 1 and 6 micron.
Yeah, 1 and 6 microns, because it covers the water band and the carbon dioxide band. That's exactly why we picked it.
Okay, and so if those comets are losing the material, as you mentioned, how long do we think they live or they will last? Do we have an idea of that? Now we have seen more of those. That's a question from Anthony Philippe Redmond.
That's a good question. Comet Reed is a very small object. It is about 500 meters in diameter. So that's something that at the rate that it's losing water right now and dust, it would not last very long. So we think that this is actually a piece of a larger object. Larger objects have longer lifetimes. So there was probably a large asteroid with water buried deep inside that had been orbiting the sun for many billions of years. And another asteroid hit it. We saw that close up of the asteroid Letitia. It's shaped by impacts, and these impacts can be catastrophic and break it up into even smaller bits. And so Comet Reed is one of these little pieces of a larger asteroid that happens to be icy, and we can see it active today. That we think that this is why it's active today.
All right. I have a question. So in the context of the formation of our solar system and the presence of water, this discovery, how significant is this confirmation that main belt comets have water?
It gives us an idea of the water content of other asteroids. So we know some asteroids had accumulated water when they formed. And we can tell that because there was a point at which they were warm enough that water became a liquid and modified the minerals and actually bound to the minerals and transformed them. And when some of those asteroids eventually get scattered into the near Earth space, and some of them hit the Earth, and we can pick them up outside as meteorites. We can study their composition. So when we do that, we could tell, this meteorite once belonged to an asteroid that had water in it. So we know asteroids had water. But what we didn't know is that asteroids saved water ice, that they could be cold enough to actually preserve that water ice. So it's a different form of water that has survived the billions of years over the solar system. So that gives us a better way to estimate the water content of the asteroid belt.
Okay. One question I heard from the grapevine recently. So we are trying to find the source of water on our own planet. Is the water came at the same time as the formation of a planet, or was it brought by comets or by asteroid? And there is all this debate based on the DH ratio, which is basically a kind of a signature of the source of the water. Will it be possible in the future to measure the DH ratio of comets, man-made comet like Reed?
Yeah, that's a good question. Earth, Mars, Venus, they all formed in a hotter location of the solar system than these asteroids that we're studying. And they likely did not have much water, at least the way that we get oceans, that the oceans formed. We think that was accumulated later in the Earth's history. And to be accumulated later means it comes from asteroids and comets. And additionally, biological material or the ingredients for life could also come along with that water. So a signature of the composition of the Earth's ocean is this deuterium to hydrogen ratio. Hydrogen's the simplest atom. Deuterium is hydrogen plus a neutron. And it's like a fingerprint of the origin of the ocean. So if we could we've studied the D/H ratio of comets, and if we could study the D/H ratio of these icy asteroids, or even the main belt comets, that would be a great way to compare them to determine, is it that comets are more likely the ones to give us the right ocean water, or asteroids? Right now, it's not sure if comets are the right objects to produce the Earth's oceans because of their D/H ratios. They have a very wide range of values. But to actually do that in a main belt comet, again, these are faint objects, and that may be a capability that not even the Webb telescope can do. It takes a specialized instrument to do that. Or perhaps we could send a spacecraft to one of these someday and see it up close, and send a lab to the comet and study that water.
Oh, that was one of my questions. So
Yeah.
You anticipated it. Good. So we have a question from Steven Schreier. How JWST studies of additional comets schedule?
Oh yeah, for sure. Oh, I love JWST is what I call it, a comet machine. It has the right instruments, it has the right sensitivity. I have other projects I'm working on with a few other teams where we have observed several comets. Expect to hear more about that. I know this is just the first paper that we got out. I think you'll see more over the summer on observations of comets with JWST, and we continue to observe them. We have more lined up, 5 more comets in the next year of operations at the telescope. So I'm very excited about seeing more comet work get to the public.
Yeah, and it will be kind of interesting to see whether or not those comets have the same amount of water, and also whether or not they have carbon dioxide. Because if the main belt comet lost the carbon dioxide over time, bigger main belt comet should have still some carbon dioxide.
Interesting.
Right?
Yeah, it's possible. Yeah. So we are looking at 2 main belt comets, and one of them is a bigger one. This one is about 5 times larger than Reed. That's a lot in terms of mass. That's a big object. So
stay tuned.
Yeah, stay tuned.
You're gonna probably hear more about Mike Kelley and his research on the study of main belt comet. I think we are gonna wrapping up, because I know you have a lot to do and you have a lot of data to process and analyze. But before that, we talk about the future. I'm curious, how did you came into this field of the study of main belt comet? What is the story that make you join this field of research, which is kind of new? The first comet was discovered in 2006. So
yeah, it really was Part of a technical demonstration. My colleague Heidi Hamill has a program to study the solar system, just demonstrate what can the JWST do for solar system science. She has 100 hours of time where she's observing, her and her collaborators observing comets, asteroids, planets, satellites, Kuiper belt objects, everything that we could think of. So I wanted to look at something faint to try to push the limits. What can JWST do for faint comets? Are they different than the bright comets that we're used to seeing? And this one had a particular, if not only was it faint, but it was just an interesting object in its own right. So that's how we got to this point.
All right. You like challenges, basically.
Yeah, exactly. Yeah.
That's the point. Like all observers, I will say, we all like challenges. The fainter, the more difficult to observe, there will be always some crazy person to build an instrument to observe these objects. So how to use it. Thank you very much, Mike. It was great talking to you.
All right, thanks.
And,
it's great talking to you too.
I hope to see you soon again for another big announcement, big discovery on the study of Main-Belt comets. They are the new type of body in our solar system which are extremely useful. They are a proxy to truly understand how comets and asteroids form. So I really like the fact that we spent some half hour to talk about this today. Yeah, so thank you. Thank you to all our viewers, wherever you are on this planet, from Normandy, France. I see that someone joined us recently, and from the rest of the world. This was a SETI Live with Mike Kelley. We talk about Main-Belt Comet. You can support our program by visiting our website at seti.org. Click on Give Now or something like this, and you can make a small donation to fund, for instance, the next study of the next space mission to visit the Main-Belt Comet. This could happen in the future, or simply to help us financially to keep this program alive and invite more people to talk about their research here. We can also simply join our social media. We are on every platform. I'm not going to name them. You know them. You can also put a thumb up on this video, tell us, write some comments, ask questions there. We spend some time to answer to your questions. So if you have any things you want to say to Mike and you don't have the opportunity today and you're watching this later on, let us know, write a question, so we will take the time to answer to this. Okay? And in the meantime, look up, enjoy the sky if you can see it. Let's see each other next week for another SETI Live. Bye-bye, Mike, again, and thank you very much.